Hi everyone, my name is Quadri. I'm a PhD student in statistics at Rice University. I work with Professor Fredri and Dr. Catherine in putting together this training alongside every other stakeholder. And I'm excited to do this video to share an overview of what Bayes is and why this matters to us. And I hope that at the end of this video, we have good understanding of Bayesian analysis and why we are looking at this statistical framework. And so we start with the question of what is Bayes, right? So most of us will make decisions based on experiences and of course new information. This is exactly what Bayes does, right? It's the product of two things. We call one of them is the prior probability, prior information, and the likelihood that is information generated from data. We multiply these two things together, and then we have what we call posterior, which is your new information. And so, like in the classical frequency statistics, where you assume that there are, repeated experiment, and then you can define probabilities based on repeated experiment. For Bayes, we don't have that, right? So we just have prior knowledge, right, based on like expert information or previous, information about some certain quantity of interest. And then we have likelihood, which is information we get from the data. We multiply this together, we have what we call the posterior. And so this is typically what Bayes is. So Bayes updates, what we know about some quantity of interest before we see data, which is our prior, with information from the data, which we call the likelihood, to give us, new improved information, which is the posterior. And so why does Bayesian thinking matter? Right now, in classical frequency statistics, the parameters are fixed and unknown, right? But in Bayes, our parameters are random variables, and so they have uncertainties attached to them. And so this helps us, to define probabilities on these random variables. And this can help us to measure uncertainty, right? To quantify uncertainty in a robust way and also measure risk. And so we can, compute probabilities, for example, that a quantity of interest would be maybe greater than or less than, a certain threshold. And so Bayesian analysis helps us with that. Also, in the classical frequency statistics, right? We know that majority of and all of our inferences are solely on the data. But for a Bayes, right, we have prior information, so our inferences are not solely based on the data. It's also based on prior information, prior experiences, and so the combination of this with the information from the data is how we have inferences from the Bayes. And so also in the frequencies, right, statistics, because we require, repeated experiments to construct and define probabilities, right? It requires large data set. But for the Bayesian framework works well with small data sets. And so this makes Bayes, very appropriate, especially in agriculture where we would usually have small data set. Also, another importance of Bayes is that, as I said, Bayes is a very powerful prediction tool, and it allows us, to examine numerous future outcomes. And of course, it is a very good framework in estimating uncertainty, which we do not get with the frequentist, approach, frequency statistic. Another thing is, of course, we know in the frequency statistic, we find what we call the confidence interval. And this is basically just, after repeating experiment, you are saying that, for example, if we're considering, let's say, the 95% confidence interval, you are saying that 95 out of like maybe like 195% of our interval will contain the true parameter. But that's not the case for Bayes. In Bayes, we compute what we call the credible interval, and this gives us probability, right? So when you say, for example, in 95% credible interval, you're saying that there is a 95% chance, right? With 95% probability, we know that our parameter would be within this interval. And so this is why Bayes is important. And so before I show you the, simple mathematical framework of what we're talking about, let me just give you a little bit of an example. So for example, if you're interested in finding, let's say we want to estimate the nutrient deficiency in our farmland, right? So again, what we'll do, first step is of course prior information. And so probably we have information on what deficiency looks like at this time, of the year in our farms, or maybe we have expert opinions, and we know that, okay, for example, the probability that you would have nitrogen deficiency, nitrogen deficiency in your farmland is 30%. And so that probability is what we call the prior probability. Now we take that probability and we combine that with the information we get from data. And so you can do some sorts of testing, right? Some sorts of nitrogen testing. And maybe when you do testing, you know that the chances that you would have low nitrogen level, given that you have a deficient farmland, let's say is maybe 80% of the time, or maybe the chances that you would have low nitrogen level, given that your farmland is not deficient of nitrogen, is 20%. So those values are what we call the likelihood, which we get, from the test, from the data. And so combining these two information, we can then find, for example, the probability that our farmland is nitrogen deficient, given that we have low level of nitrogen based on the test we do. And so this is a typical example of what Bayes helps us to do. Another example is, let's assume we want to estimate crop yield, right, in the farm. And so again, a prior information can be that probably in previous years we know what the average crop yield is like, for maybe, for example, sorghum or legumes. We know what it is, and of course we can have a distribution of that, for our like our farmland in crop yield in like different years. So that's the prior information. And so we can take that with data that we collect currently. So we can collect data on the yield of, let's say, sorghum in our farmlands now. And so with that information that we have now based on data with prior information that we can combine both information to get a posterior, meaning that we can now find, the average crop yield given the data that we have. And so this is what Bayes allow us to do. And so quickly, I'm going to share with you a slide of how this works. So as I said initially, it's basically just the product, of two quantities. And so we can see here the P here is probability. And so if you look at this is of course the prior probability, right? The prior probability. And so based on the example I was mentioning earlier, so this could be, if our quantity of interest, let's say, is the nitrogen deficiency, and so this would be prior information, maybe expert, maybe we talk to talk to a farmer or an agronomist, and they have information on what the nitrogen deficiency looks like. So they can tell us, so the probability of that your farmland is nitrogen deficient in a season like this is this quantity, this amount. And so that's your prior information. And then we have the likelihood. So given that the farmland is nitrogen deficient or not, what's the probability that I would have low nitrogen level. And so that's what we call the likelihood. And so of course you can obtain this based on data, or based on testing, as we were as the example talked about, right? And then so the product of these two is what gives us the posterior. And the posterior here is saying that given that I have low level of nitrogen, what's the chance that my farmland, is nitrogen deficient? And so that is what we call the posterior. And of course, with this posterior, we can compute credible interval, we can find uncertainties and all of those. We can find probability, compute risk in terms of like if it is below or above a certain threshold. And so there's a lot of things we can do with this posterior probability. Now, if you look at this, you would see that is, of course, the what we call the marginalization constant. Now, usually in practice, people kind of like ignore this, right? Basically, because this helps to make this a probability density. And so that's what this is, just to kind of like marginalize this so that this becomes a probability density. And so that's why it's a marginalization constant. So it's a constant. And so usually in practice, they would say this is approximately these two, right? Or it's proportional to just the product of these two. And so this is some of the things we will be looking at in the training. There are tools that can help with this computation. There are packages in there that can help, and we will be learning that in the training workshop. So thank you, and see you all. Bye.